Let's look at the case where a board is rotating with a constant value of omega until a small box that's resting on it slides off. We're given the coefficient of friction, which is holding it on. Our goal is to find theta max right here, where that box slides. Step 1, we need a free body diagram. Step 2, Newton's second law, MA. On our free body diagram, we have mg straight down. We have a normal force up, perpendicular to the board. And we have friction, mu F N, acting up the incline, where we can call this r hat and this theta hat. And we'll be okay calling this direction positive theta hat as long as we stick with it for the whole example. Let's come in here and break up mg into its components. We'll have a theta here and there. We have mg cos of theta in this direction. And mg sine of theta in the r hat direction. And we won't need to use the mg. Summing the forces into theta, we'll have ma theta. This is the positive direction. We have mg cos of theta minus Fn equals m. Recall in polar, this is 2r dot theta dot plus r theta double dot. The board moves down with a constant angular velocity, so r double dot is 0. And it's not sliding yet, so r double dot is 0. So it turns out Fn will be mg cos theta. It's non-accelerating. So that's similar to a statics solution that you might have seen for inclined planes. If we look at the r hat direction, again, here's positive, mg and again recall this r double dot minus r omega squared. If it's not moving, the box hasn't begun to slide, r is not changing, so that's 0. We know Fn, and we'll get mg sine of theta minus mu mg cos of theta is minus mr omega squared. Can divide through by m. We could divide g through as well. Interestingly, this is a sub c over g, an acceleration ratio. now I'd like to get rid of this negative, so let me run a -1 through here, and we'll get u cos of theta minus sine of theta is r omega squared on g. And technically this is our solution, but we have a problem here that we want theta, and it's buried in two functions. This is a common problem that we'll run into when working on these equations, where we'll have a cosine and a sine together that we're trying to solve for that variable inside of there. And there's a few ways to solve this. One is to move sine to the other side and square both sides, in which case this can be written as 1 minus the sine squared. And we'll get a function that's all sine based. It's a quadratic equation. Another technique that works well is to use the trig angle sum formulas, where here we'd like to take these coefficients, and here there's a coefficient of 1, and we'll define an angle phi to be mu, which is one of our coefficients. This leg can be the other. And this side we'll call r, which is the square root of 1 plus mu squared. And from this triangle, we can define sine phi as mu over r, or mu is r sine phi, and cosine phi is 1 over r, or 1 is equal to r cosine phi. What we'd like to do is take these values and put them in over here. So if we do that, we'll get r sine phi for mu minus, now this 1 is r cos of phi sine of theta, and it's r omega squared over g. And we can factor out the r and divide that over to here. And if you look, we've got that term right here. So for a negative, we'll keep the negative, and we can write this as a single function, sine of phi minus theta is equal to r omega squared on gr. And our goal was to find this theta value here. So to solve for that, let's bring this up. We'll get that phi minus theta is sine to the minus 1 of r omega squared over gr. Subtract phi over, run through with a -1, and we'll get, finally, theta slip is phi minus, if I reverse this order, sine to the minus 1 of r omega squared over g square root of, now r, recall, is 1 plus mu squared. Phi right here is based on our triangle up here. Now, a nice way to write this would be to write it as a tangent function. It would be opposite mu over 1, and you might recognize that as the friction angle. From statics. So phi, therefore, is tan to the minus 1 of mu. So it's the friction angle minus whatever this works out to be. So let's take a look at an example. Let's have omega be 2 radians per second. Let's take a mu of 0.8, something fairly high, and a radius of 1/2 of a meter. From there, we will get phi is tan to the minus 1, 0.8, which works out to be 39 degrees. And then this angle here, we can call it beta. It's a dynamic angle. And beta will be sine to the minus 1 of 1/2 of a meter. 2 radians per second squared. 9.8. Square root of 1 plus 0.8 squared. And that will work out to be 9 degrees. So we find the angle where this slips will be phi minus beta, which is 39 degrees, the friction angle from statics, minus 9 degrees, the dynamic angle, which is 30 degrees. It's the angle of slip. If we think about that, it sort of makes sense that it should be lower, should be decreasing it. Rotate down with our box on here. We have our friction holding it up and mg sine theta pulling it down. We have an a sub c here. And this a sub c is creating an acceleration, and this box does not want to be accelerated. It has an inertial resistance to that. So its resistance to that acts like a force, and it tends to want to pull the box off the hill. As a result, if this was 39 degrees, our static value, we will slip off the incline at 30 degrees because of this extra inertial response inside the system. So it sort of makes sense as this thing is rotating, it has more forces trying to, more dynamic forces that are trying to pull it off the edge of the board. Now, an interesting question could be, will this work on the way up as well? Let's take a look at that. Let's take a look at the case of the box sliding down the hill while rotating up. So we have omega going up, m. We're looking for theta up. And again, our free body diagram. Mg down. Fn out. And mu Fn acting up the hill. And as before, we'll break this mg up to components. That's theta, this is theta. This will be mg cos of theta, mg sine of theta. And it's basically the same free body diagram. call this the r hat, and this time we'll call this the positive theta hat, the direction that omega is carrying that. Sum of the forces in the theta is m a theta, which will be m 2r dot theta dot plus r theta double dot. It's moving with constant omega, so that's 0. It's not slipping yet, so r dot is 0. So again, we see it's a static case, in which case we know that Fn is simply mg cos of theta, just like before. The other direction, we'll get, now in this case the box is trying to slide down the hill, right? So we have mu Fn minus mg sine theta is equal to m r double dot minus r omega squared. It's not moving yet. R double dot is 0. We know Fn is mg cosine theta, so we'll get mu mg cos of theta minus mg sine of theta is m negative r omega squared. There's an m in all the terms. The m's can go. There's a g here. We can move that to the other side again. And we'll see now the only difference from before to what we had before these are still the same. The only difference is that's now negative. Let's see how that will affect our final result from before. So before we had that, this negative will stay right there. As a result, recall that sine of negative x is negative sine x. So having that negative there will make this positive outside, and that'll be the only change, which will allow us to write this equation as plus or minus for up versus down in terms of the rotation. Therefore, the numbers themselves won't change. We found before that static was 39 and beta was 9. So theta up the hill will be 39 plus 9, which will be 48 degrees. And again, this should make sense if we look at that. Here's the 0 case. And on the way down, at 39 was the static. But we found that accelerating it caused the box to slip off sooner at 30 degrees. On the way up, there would be a static case of 39. But we can go further past that now by 9 degrees, all the way out to 48. And again, this should make sense. Here's the box, and we have an a sub c towards the center. So the inertia is trying to pull the box up. Its resistance to this acceleration is trying to lift the box off of here. You can see that if we spun it fast enough, it would fly up and off the ramp potentially. In our case, we're trying to do it at a constant omega and see what effect that has. So for our moderate values of mu equal to 0.8, omega equal to 2 radians per second, and r equal to 1/2, we find that that's the range. And with that we have an equation, this equation, which will explain both cases for up versus down. Now there's an interesting case that we can look at here. Can it slide out? I guess this would be up and out. We'd be rotating up, and potentially the box could slide out. And that's an interesting scenario. First case, it would have to have a larger omega than we have now in order to reverse that motion. So we need a large omega. So let's find omega max for any given angle and see what that effect is. So for sliding up and out, the board is rotating up and our box will slide out. In which case we have similar forces as before. We know that we're going to have an mg sine of theta pulling us down the hill, mg cos of theta acting into the board, Fn up. And what's different now is if it's going to move up, friction will also be down the hill. So mu Fn in the same direction now. Since there's still no acceleration in the theta direction, we know that Fn is still mg cos of theta. And in the r hat direction, we will get minus mg sine of theta minus mu mg cos of theta is m r double dot minus r omega squared. And as before that goes, you can divide through by m, divide back through by g, and we have negatives everywhere, so we multiply through by a -1, and we'll get, and let me switch this order just so it matches the other one, mu cos of theta plus sine of theta is r omega squared on g. This would be for up and out. And again, you could try to find that angle. Let's solve this for omega. Omega max for any given angle will be g over r mu cos of theta plus sine of theta. So that's the omega max to slip at any angle. Now our desire here is to find the maximum for this, so let's take the derivative of both sides, in which case we'll get 2 omega times omega dot is g over r negative mu sine theta plus cosine theta, and the derivative will set omega dot equal to 0 for a max min condition. So if that's 0, we can divide through by that, and we're left with just this. So we'll have, if we bring this over and make it an equal sign. Mu sine theta is cosine theta. Divide through by the sine of theta. And we find that we have 1 over the tangent here. So the solution is that tan theta omega max is 1 over mu. It's the inverse of the static friction angle. Out of curiosity, we can solve this for ours. Theta omega max is tan to the minus 1 of 1 over 0.8. And we'll get 51 degrees from that. And if we plug the 51 degrees into here, we'll find that that omega max is 5 radians per second. Oops. 5 radians per second. Which is greater than the 2 that we had before. The trick is it will slip off before it reaches it. If we look at the 0 degree case, we have mg down, Fn up. Again, no acceleration in the theta direction, so these are equal to each other. So this will be mu Fn. And from here, we get mu mg cos of theta, that's mu Fn, is equal to, and it's negative r m omega squared, our acceleration term. The m's go, the negatives go, and we find omega at 0 degrees is the square root of mu g on r, which for, again, our numbers will work out to be 3.9 radians per second. So we're not going to get a chance to reach the maximum. The minute we start to move this thing on flat, it's going to shoot off if we try to rotate it at 5 and we never get a chance to reach that. In fact, we could show that as this starts to move up, omega is going to continually increase to some maximum value, which we could find. So we have omega max squared is g over r mu cos theta plus sine theta. We found that the angle where omega max will occur will be at tan to the minus 1 of 1 over mu and we found that on flat at 0 degrees we found that omega 0 will be the square root of mu g over r. Which for our example, this worked out to be about 4 radians per second, and this worked out to be 5 radians per second. The problem is we couldn't pass the 0 point at 4 radians per second. We're not going to get a chance to reach that 51 degrees. where it would be 5 radians per second. And again, it's driven by the fact that omega is a constant. If we had an alpha here, we could accelerate up to that point and make it, but our premise was that it moves with constant speed. Now, another way to look at this, we could redesign the experiment and maybe we could come from the top down and see if we can make it there. Now, to do that, we'd have to invent some type of a support here so our mass could sit and it would rotate downward from the top. If we look at the top, our free body diagram is mg down. There'd be no normal, therefore there'd be no friction, and that's our entire force. So at 90 degrees, we have, again, r hat direction. We have negative mg is negative mr omega squared. The other terms are 0. The m's drop out. So we get the omega at 90 degrees will be the square root of g on r, which given our values is 4.5 radians per second, which is again less than the peak at 51 degrees. So it appears that you're not going to be able to reach this maximum on the way up or on the way down if we're held at a constant omega. So we can say then for constant omega, omega 0 is the square root of mu g on r, and omega 90 is the square root of g on r, and since mu is generally less than 1, we can say that omega 0 will always be less than omega 90. Omega max, it's g over r mu cos of theta plus sine of theta, and this is squared, and notice that is the 90-degree value squared. So we get that omega max squared is omega 90 squared times mu cos theta plus sine theta. And for any reasonable value of mu, omega max will be greater than omega 90. Therefore, omega max will be greater than omega 90, which will be greater than omega at 0. For reasonable values of mu. Now we could look at the most extremes. Mu equal to 0, no friction. If we have no friction, omega 0 will be 0. It slips right away. Which makes sense. There's no friction at all. You try to move it and it's going to move. And omega max, if this is 0, we get that omega max squared is omega 90 squared sine theta, in which case that max is at 1. Omega max equals omega 90 at 90 degrees at the top. If we look at the other extreme, where mu is equal to 1. Let's give it a lot of friction, very, very sticky. If we look at that, omega 0 is the square root of mu g on r, which will become the square root of g on r, which was omega 90. So they'll be equal to each other. And then omega max, which is omega 90 squared, mu cosine theta plus sine theta, where mu is 1, we find that this will be greater than or equal to 1 for all angles. At 0 degrees, this is 1, and it's the same at 90 degrees, and it has a maximum value at 45 degrees of the square root of 2. So if we plug that in, we get omega max squared is equal to omega 90 squared times the square root of 2. Therefore, omega max is equal to 2 omega 90 for the extreme case of mu equal to 1. So under all cases, we're not able to reach this at a constant omega if we start at 0 or we start at 90. We would have to have some alpha to reach that value. And for fun, you could try to find that alpha as omega final minus omega initial over t. And if we want to make an average approximation, you could plug in some values and see if we can get it to reach that value. But our model had it as a constant. Thanks for watching.